Okay, we're going to continue with this again. So after the first video where I ran out of battery power, and the last video, no wait, the first video I ran out of space on the thing card, and the second video the battery just cut out because I hadn't charged it up. I kept assuming that it was fully charged all the time, because why would it not? Don't things run on magic nowadays? Anyway, so we were back here. I think we were up to this point. I'd gone through stuff. I looked at the video, and of course everything was all over the show. We're not going to zoom in, because otherwise you can't see anything. Too much writing stuff. And no, I'm not going to change it so that the video is the other way around, even though that would be much, much easier. I kind of like the way it is now. As I said, that would require post-processing, and I can't be bothered. The only post-processing I do at the moment is just switching the video format, so it's a bit easier to upload. Alright, so we're back here, and we're going to turn this on, and we're going to learn a little bit about using a multimeter. So this is like a very, very, very cheap multimeter that you can buy off the internet and from various places. It doesn't cost very much. I think it's like $10 or $15 or something. I'm sure it doesn't work very well for, like it says, it goes up to 600 volts. I don't think it's very effective. I doubt it would be very good at measuring 600 volts AC. But we're not, I'm not going to use it for anything over like 20 volts. So let's just go here. So to test the voltage, we test across the component. So I'm testing the voltage drop here. So we're thinking about the voltage drop. So at here, the voltage, well, I don't know what the correct term is, but we've got 5 volts here to 0 volts here. So there's a 5 volt difference between these 2 points. So we're going to say this is 0 volts and this is 5 volts. So if I measure this, I should bring this onto the thing, and we should activate the backlight. The potential difference between the two is 5 volts. There won't be exactly 5 volts because there'll be losses in the wire, because wire has resistance too, and nothing happens. That's a bit of a shame. Why does nothing happen? What is happening? Oh, because I haven't actually created a circuit. So I took the LED out. So now this is actually doing something. So we are using up electricity, and if we measure it, it should say, this is 5 volts. That's pretty cool. So 5 volts is coming out. So not a lot is being lost in the wire. So that's quite neat, and these things work fine. And again, if you swap these things around here on these little power adapter things, it will go down to 3.3. Except that one's not quite 3.3, it's 3.26. So it's not quite good at the, not quite as good. Something's not quite as good. Probably this isn't very accurate. And you can also use this thing to test the resistance. So here's another resistor. So if I turn this one down, this one's not auto ranging, so you have to kind of choose the range that's roughly correct. So I don't really know what that is. So we'll start with 20,000 K. So with the resistors, you've got to be careful, because you don't want to hold it like this, because that will use your body. So I think it has to be lower than that. It will use your body for some of the power, some of the current to go through. Got to stop saying power. And so getting it. So this one says it's 200 volts. 200 volts. 200 ohms of resistance. So if I touch it with my finger, you'll see that it's okay. It's the same thing. That's because I've got reasonably high, but very high. No, there you go. So the resistance that goes through me is about 500,000 ohms. We're jumping around a bit. Probably goes to my heart rate. So I was kind of keen on doing something where you can measure this accurately. Always going up to like a 1 million ohms. So not a lot of current. We haven't gone to the parallel circuits yet. So, but on some of these things, like if you're measuring a 150,000 kilo ohm, 150,000 ohm resistor, or even a 500,000 ohm resistor, then if you touch it like this and hold it, it's going to give you a wrong indication. So yes, so anyway, so we've measured that. So now they're just the interesting thing. So we can't measure current so easily. We have to actually put things into the circuit. So you measure current, and it's just a pain because you have to swap things around. So I'm not going to do the current. You can kind of get away, because once you know, if you know the resistance of something and you know the voltage across it, then you can work out the current going through it. Again, thanks to our friend Ohm's law. So you don't always have to, where's my V equals IR? You don't always have to actually directly. In fact, I think that's how these things measure current. They have a thing called a shunt resistor, which is like a 1 ohm resistor, and it just measures what the voltage is across that resistor. So there we go. And if you don't ever change it to current, you should be fine. The one thing is you should never set this to current, I think, to read the current and then do what you just did with the voltage thing, because that will possibly end up blowing this thing up. So blowing that up. I'll explain that in another video. Otherwise, if I do that now, we'll never get to anything else. So the most important thing, so the two things I want to quickly get done is to talk about what happens when you have two resistors in series. So I'm going to go back to drawing them like zigzags. So say you have that, I'm just going to quickly, so 100 ohms and 100 ohms. So what did I do with that packet of, oh my goodness, it's a packet of 100 ohm resistors. Like a lot of 100 ohm resistors. So these are the 1/4 watt ones, so you can tell by their size. And we're going to quickly turn that off. It doesn't look like it's doing anything, but it is in fact wasting my batteries. I should probably charge up my awesome little very low capacity rechargeable one. Or I could just plug it into a power thing. So I'm going to make a little series circuit with this. So there's a couple, what did I do? Oh my goodness, I've lost my little 100, where am I going to get that from? Where am I possibly going to get any more 100 ohm resistors from at this time of night? If only I had a large container full of them. Alright. So this is a terrible looking circuit, so we're going to have to come up really close. So this is in fact a kind of like this circuit, except in this case I haven't drawn the power. The power, the battery, the voltage supply. So in here we're going positive from this bit, goes into this little, down this little wire here, into this wire, through this little resistor, and then through that resistor, and then back down to ground. So there's a path from the 5 volts down to ground, and so things will travel through. So remembering from the last video, I was kind of saying that resistance is like, not resistance, like the voltage and the current. Voltage is kind of like how much money. So if we have a voltage difference of 5 volts, so between here and here, there's a voltage difference of 5 volts. So it's 5 volts here. I'm just going to write it on the side. 5 volts and 0 volts. So 5 volts to 0 volts here, created by the battery, this potential difference. Then you've got 5 volts to spend to get across here. It costs $100, 100 units or something, 100 ohms to get. So the cost is 100 ohms here per, I don't know how to say this. Is that the best way of explaining it? All right. Well, the reason I want to talk about the money sort of analogy is that you got to spend this 5 volts across these two resistors in such a way. So the important thing here is the current law. I can't remember who was it. Probably Kirchhoff's current law. That the current that goes all the way through here on a series circuit has to be the same all the way down here. So this is the first important fact. The current doesn't change as you go through here. And that kind of makes sense, because otherwise there'd be bottlenecks. If you imagine it's little tiny little electrons bumping along slowly like this, they can't all sort of pull It has to be moving kind of roughly at the same sort of rate all the way through, because otherwise they'd be clumping up. And they don't clump up. Well, they might clump up like in very minute little seconds, you know, like a tiny, like a nanosecond, even smaller than that. But in general, like when you're seeing it, they're not. They're sort of spread out and they're all moving at a constant rate. So you could spend 4 volts here and then 1 volt here. But 4 volts will get you more packages or more little boxes going through here than it will going through here. So that's not really what's going to end up happening, because you'll get all these packages through here and then you won't have enough money to move the packages through here, because they cost the same. But if you spent most of your money on this, you've got like 4 times as many through this part, and but you've still got to get them all through here. So it won't happen this way. So what will happen is you'll spend whatever you need to get the same amount of boxes through each area. So in this case it will turn out that maybe I should do what the total. I'll tell you what the total. So with resistors, if you want to work out what the total resistance is across this whole area, the total resistance, and this is going to be, we could do this another. We'll do it 2 different ways. So we'll come back and we'll think about this. But for now, I'll just say the total resistance is really easy to work out, and it makes a lot of sense. Is that if this much costs you this, you know, the resistance to go through here is this much, and the resistance to go through here is this much, then the total resistance is going to be this resistance plus this resistance, because you've got to do both little things. So if you're doing like an obstacle course, the total, you know, things you have to do is going to be this obstacle plus this obstacle to get through from this side to the other side. So the more things you add in, the higher the resistance is going to be in total. But say we've got 100 ohms here and 100 ohms here. Well, what's the way that we're going to get the same current going through each thing? Well, we'll have to spend the same amount of money or the same amount of voltage on each thing. So in this case here, we're going to get, I'm going to write it this way, 2.5 volts will go through here. Right, and then we'll spend the remaining 2.5 volts to get through here, down to 0. Because if we did anything else, then we'll get more boxes in one area going through than we would in the other area, and then they'll be like bunching up, and that won't happen. And so it will work out that the voltage will be 2.5 there and 2.5 there. And we'll quickly go through and we'll test this. So we've got this exact circuit here, and we can test this exact thing. So if I turn it on, and I get out my little voltmeter, well, not my voltmeter, my multimeter, but it's acting as a voltmeter. And I'm going to set it on this one because this is a very, very cheap one, and I have to say what kind of range it is. To 20 volts, because 2 volts is too low, because I expect it to be over 2 volts each, but it's going to be less than 20 volts. So now I will touch 1 to here and 1 to here. You're going to find it says negative. So it says on the thing negative because I've got these around the wrong way. So if you put the red one towards the higher voltage area and the black one towards the lower voltage area, you get the right sort of thing. It doesn't matter, you're not going to blow it up. It just will say negative if you get it the other way around. And sometimes you might, you know, this goes towards your ground point, and sometimes things go lower than the ground point, so you will get negative values. So as you can see, it says exactly 2.5 for that one, and it will say exactly 2.5 for the other one. So what we need to find, do I have any more? Wait, I do. I don't have, oh, you have to be kidding me. I have this packet of things for another project, and I keep putting them everywhere, and then they just disappear. Okay, where would I have put it? Sigh. Alright, this will make the maths a bit hard, and I forgot to bring a calculator in here. Oh, what a load of bother. Right. Surely I have it right here. Sorry, give me a second to ramble and ramble and ramble. And it always turns out that it's staring me in the face. Okay. Well, I had a box and it had 300 ohms resistors, and that will make the maths easy. But I don't. So we'll have a look at what's in here. Actually, we'll just steal this one. No, I won't. Ah, that makes me sad. So sad. So what are these ones? Those are, I think, 100 ohms. Let's just check. It's probably going to be down there. So I have this one here. It doesn't matter that it's a bigger one. Oh no, it's a much bigger one. Oh, I've got the whole thing on. It's a 240. Well, that's still not going to make the maths easy. So I'm going to stick. Well, that just rubbishes it. Oh, it's a calculator. Okay, we don't have to worry. We can just do the maths. What's a little bit of maths between people? Not a lot. I just don't understand how I can manage to lose things every 5 seconds. Alright, we have to do this quick because this is rambling too much. Okay, here we go. So now in my circuit, I'm going to change one of these things. So we're going to take away all these. We should have some white out. And we're going to make one of these. It doesn't matter which one it is. So we're going to make one 330 ohms. Okay, so in this case, this one is still 100 ohms, and this one is 330 ohms. And so, if you think about it, it's going to cost a lot more. Right, so if we want to get the same number of boxes through here, the cost is higher to get them through here than it is to get them through here. So, if we're getting the same number of boxes all the way through, we're going to end up spending more of our voltage on the 330 ohms to get the same number through. Alright, and we can actually, there's like lots of ways of working this out. We'll do this we'll do this in a separate way. We'll do this one way, we'll do this the other way. So the first thing we know, so we can do this with the maths, we'll do this with lots of maths. So as I said before, the total resistance is going to be this value. How much time we've got left? 11 minutes. This is going to be a 30-minute video and we haven't even got onto LEDs yet. So 330 plus 100. So the total resistance is 430 ohms. So 430 ohms is the total resistance. So RT equals that. And we know what the voltage is across the whole thing. It's 5 volts. So going back to V equals I times R. So 5 equals I times 430. So then I should have done this on a separate piece of paper. Okay, let's do this on a separate piece of paper. So we've got 5 equals 430I. So I equals 5 over 430, which equals, let's get out the calculator, which used to belong to somebody else. On. Okay. So I'm going to do, actually, 430 divided by 5 is 86. So that equals 1 over 86. Okay, 1 over 86 amps. So that's how much current is going through. And so now that we know this, I know you're going, why don't you do the actual decimal value? Why are you still keeping it as a fraction? Because it will make the maths easier at the end. So we've got 1 over 86 amps. And so now we can actually work out the voltage across each thing. So remember, again, V equals IR. So I'm going to call this is R1. R1, and this is R2. So we know several things now. We know that R1 equals 330 ohms, and R2 equals 100 ohms. And we also know that the current equals 5 over 430 equals, why did I write this whole thing out again? 1 over 86 amps. So 1 over 86 amps, which is probably like some 0.13 something. Some horrible number that we don't want to write out. So we now know what's the voltage across resistor 1. Well, we're going to call that one V1. And so we know that V equals IR. So V equals IR, V equals IR. So I know that it equals 1 over 86 times 330, which equals, and in this case I will just, which just equals 330 divided by 86. So 330 divided by 86 equals about 3.84 volts. Right? And V2, well, we could cheat. We know that the total amount that we're spending is 5 volts. So if we've already spent 3.84 to get across that one, then the remainder is what we're going to be spending to get across the other one. But we'll just check. So in this case, V2 equals 1 over 86 times 100. So I'm not going to write the whole thing out again. So that just equals, actually I'm just going to write 100 over 86, which equals 1 point, I'm going to guess. I'm going to do it on the calculator. I'm doing it on the calculator. We've got to do things. I had a job once for a guy, and we were doing IT support. And he kept trying to check algebraic proofs by going through and plugging in, and it's like, well, it's obvious that you don't have to do this. I don't know why I just thought of that. I know what it is, because I actually did it on the calculator when I could have just done that in my head. So that's 1.16 volts. And you might be able to pick out that, in fact, what you can do now, what a mess, like seriously. Alright, so we know that the voltage across the 330 ohm resistor is going to be about 3.84 volts, and across the 100 ohm it's going to be 1.16 volts. So we'll quickly just check that, and then we'll come back. Oh, I've gone and lost it. No, I haven't. Okay, here we go. So we're going to pretend, it doesn't actually matter, we could have swapped them the other way around. The ordering isn't particularly important in this case. So there we go, it's very obvious which is which. And then we're going to measure the voltage. So put that there, and then we'll turn the lights on so that you can clearly see it on the display. And then we're going to test this one. So this is the 330. We've got 3.88. So not quite what we were hoping for. And the other one will be, it's a bit harder because it's a bit flimsier, 1.18. That seems a bit odd, doesn't it? Because 1.18, hold on. See what I mean? I don't think you can really trust this. We'll put it at 2 volts and it might be a bit more. So when you set it to 1.26, it's 1.161, which is pretty much spot on, and it gets a little bit less accurate here. So 3.87. So we predicted similar values. So our predictions were 3.84 and 1.16. So we got that one. But of course, this is just inaccuracies, and there's resistance in the wires and all that kind of stuff. So it's pretty much spot on what we were predicting. You wouldn't expect it to get it exactly right. There's always real world stuff. So anyway, the last thing we're going to do is that you can actually just do this. There's a simpler way. And if you're doing like the algebra in your head, you can probably see. I'm sure we could do a nice little proof, but I'm just not going to go through the proof. I'm just going to finish and say, you can actually just work out what the voltages are by looking at the ratios of, so right here, the ratios of resistance. So the total resistance is the total resistance is 430 ohms. Alright, and so the ratio is 100 over 430, not the ratio, and 330 over 430. So actually that's just me writing out everything, but the ratio of the voltages, the two voltages across these things, is going to be the same ratio as the two ratios of the resistances. So basically, the ratio of the resistances is going to be 300. Well, that actually that makes perfect sense. So the voltages here, so V1 equals that, V2. I got those around the wrong way. Okay, V2, V1 equals that. But if you divide wait a second, we'll just do V2 divided by V1. If we do V2, then we get, should I have done the other way around? I think I should have. V1 divided by V2 equals 100 over 430 divided by 330 over 430. And if you can't do math so well, that will equal 100 over 430 times 430 over 330. So the 430s cross out and you get the same thing you had before. So the ratios will be the same. So if you knew the ratio, if you knew that was 500, is that a really good way of understanding it? Probably not. We'll just leave it there. But you can roughly tell. So if they are the same, then you're going to split them up evenly. If they are larger, then you're going to get more voltage being used across the thing with a higher resistance. I think that's the most important thing. And we'll finish it there. I don't know if that's really helped anybody at all. But it's good to talk about that and to draw messy little pictures. And then the next thing, the one thing I really wanted to get to, so then we can go back to this little project, is actually what happens when you use a resistor and how you work out what the, not a resistor, when you use an LED. Where's my big bag of LEDs? Sigh. Here we go, here's a whole box of LEDs. So there's my funky green ones and some funky red ones. So next time, so this, just so you know what we're going to do next time, though I really want to, we're going to do a repair job as a preview, a repair job on this Sony Walkman from the 80s or 90s, probably the 90s, and to get it to work, because I don't think it's a very hard problem. It's not really an electrical, it's not really an electronics problem, but we get to take it apart and have a look inside and see what we can do to fix it. It's pretty obvious, but I'm not going to say what it is yet. But whether or not I have the parts, that's the thing. So if we put these things in, how does this work when we have this this thing from before? Anyway, this is called a voltage divider, and I'm going to come back to this an awful lot, so we won't forget this bit. So voltage dividers, I think, are a useful way of understanding things that aren't even voltage dividers, but they come up all the time. So we really have to get a good understanding of that. So anyway, we've got 33 seconds left. That was 29 minutes. And so I will see you next time when we have some stuff to say. Bye!